In this video, we are going to talk about the C# exception handling mechanism, which is called try-catch. I'm going to talk about which exceptions you should be catching, which exceptions you should be ignoring. I'm going to talk about a new feature of C# 6 called exception filters. And I'm going to talk about another new feature of C#, a tiny little feature, but it's kind of fun, called the name of feature. So let's look at some code. I'm going to briefly review how exceptions work in C#. We've seen this a couple times already, but it bears going over again. If you have some operation which is illegal, like for instance in this code, I'm going to ask for the length of a null string, right? Then we know that if we run this code and we try to get the string, try to get the length of the string, then we get an error that says object reference not set to an instance of an object. All right. We also know that we can throw our own exceptions. So here, for example, I'm going to call a method, my method, and I've passed in a null name. And I'm going to say, well, let's throw an argument null exception in that case. Rather than dereferencing it and getting a null reference exception, let's throw an argument null exception and say, this guy's bad. Right? And sure enough, the program comes to a screeching halt and says, value cannot be null. All right. So that's all well and good. So far, every exception that we've seen in this course has been what I call a boneheaded exception. And this, I would like to emphasize, is my own taxonomy. This is not a sort of a standard programming language idea of boneheaded and fatal and exogenous exceptions. I've just found it useful in my own programming, trying to understand how exceptions work. So what do I mean by a boneheaded exception? Why do I say that every exception that we've seen so far has been boneheaded? Well, I mean the exceptional condition, the thing that went terribly wrong that caused the program to halt, is 100% avoidable. You never need to dereference null, right? You can always say, does this dictionary contain this key? You can always say, is this index within the allowable range? You can always say, is this receiver valid? You can always check for these things. So there's no excuse for getting it wrong. If one of these boneheaded exceptions is thrown, somebody has a bug, right? The code is wrong, right? And you should just fix the bug. The exception is the big flag that is waving that is saying you have a bug in this code. Now, by a fatal exception, I mean something has gone really, really horribly wrong, and that the process is likely to be terminated as a result. So for example, every process has a virtual address space associated with it. That memory is allocated out of that address space. Note that address space and RAM are different things. People often get them confused. But when the operating system says, hey, you're out of memory, what they really mean is, you've run out of address space in this process. There's nothing you can do about it, right? It can certainly happen. .NET will produce an out-of-memory exception. What are you going to do? Almost everything that you can try to do will make something worse, right? The process is going down. You don't want to handle the exception. You don't want to try to make it better. You can't make it better. I often tell people it's like, oh, my house is about to be demolished unexpectedly. I guess I'd better do the dishes first. No, you don't want to do that, right? You want to get the heck out of the house. It's going down. Build yourself another house somewhere else. Finally, the most interesting class of exceptions are the exogenous exceptions. And exogenous exceptions are exceptions that happen due to something totally outside the control of your program. So, for example, somebody unplugged a network cable. Your disk ran out of disk space. The website that you're trying to connect to get some information off of is down. Just something out in the outside world has gone terribly wrong. You should expect that sometime it should go terribly wrong. You can recover from that situation, and you can keep your program running. So let's see how we do that in C#. How do you deal with an exogenous exception? Well, the most common situation in which exogenous exceptions arise is opening files. So we're going to talk for a little while about how you open a file. So there's a very handy method in C# called file.readAllText, and it does exactly what you would expect. You give it a string that has a path to a file, and it opens that file, it gets all of the text out of that file, and it puts it into a string for you. Super useful. The problem is, what if that file doesn't exist? Here I'm trying to open a file called hello.txt, and I'm going to try to open it, and we'll find out in just a moment what's going to happen. And sure enough, we get an unhandled exception, file not found exception occurred, could not find the file hello.txt. So how are we going to deal with this? The way we deal with this in C# is to use what's called a try statement. A try statement, like many of the statements in C#, takes a block of statements that it will then execute, unlike the if, while, do, for, and for each that we've already seen. The body of the try must be a block. In each of those other statements, the body could be a single statement, or it could be a block, which, as we discussed last time, a block is a single statement. In the try statement, the body must be a block. The way a try statement works is, if the code in the block throws an exception, then control passes immediately to a block called the handler. OK, now what I just said, the control passes immediately to the handler, that is actually a lie. But we will explore why it is a lie later on. So for the point of the pedagogy of this video, let's just assume that what I said was correct. Control is going to pass immediately to the handler. Well, let's take a look at that. The try statement that we're going to write has this syntax. So there's a try block, and then a bunch of statements inside the block, and then immediately following it, a catch block, and then a bunch of statements in that block. And so like the try, the catch also has to have a block. All right, so let's try this program again. I've started up Visual Studio again. We'll step into it. And this time, rather than just calling read all text like this, I'm going to do it inside a try block. Now, we know that this is going to fail because the file is still not there. Now, let me just make a little aside here and say, isn't this really a boneheaded exception? Could we have avoided the exception? Right? We could have tested something for null and avoided the null dereference exception. Couldn't we test to see if the file exists before we open it, and thereby avoid this exception? And the answer is, well, yes, you could. You could write code that tests to see if a file exists. But that wouldn't tell you that you could open it. The file might exist, but it might have a bunch of permissions set on it that don't allow you to open it, but do allow you to determine that it exists. Right? So then we would have to check for that as well. But that still doesn't solve the problem. Right? The file could exist. We could check to see if it exists. And then in the millisecond between when we checked to see if it existed and it was opened, the operating system could delete the file, or change the permissions on the file. Or the file could be on a network, and the network cable could get unplugged in that millisecond. Any number of things could happen. There's sort of a general defect pattern here that some people call the talk-to pattern, the time of check versus time of use pattern, right? Where you check something, and then you use the fact later on that you checked it earlier, but the world has changed. So in general, you can try to make it better. You could write a bunch of code here that checks to see if the file is there, and if it is there, that you have permissions to open it, and all of that kind of stuff. But really, you can't prevent the world from changing from underneath your feet. So the best thing to do is to simply accept the fact that these exogenous exceptions are going to occur and handle them appropriately. And so that's what we're going to do here. All right, so I'm going to attempt to read this file. The file doesn't exist. It's going to throw an exception. And instead of getting this exception dialog that we should now be very familiar with, control transfers immediately to the catch. Okay. And then I'm going to say, oh, well, instead of the file contents of the file, if the file can't be read for some reason, I'm going to say file was not found. Now, again, maybe this is not great, because maybe the error was not that the file was not found. Maybe the file was found, but we couldn't read it for permissions reasons, or whatever. It's hard to say. You want to be careful when you are reasoning about code that is in an exceptional situation, because by definition, it's exceptional. Something has gone exceptionally wrong here. All right, so we can now write out the file contents, and our program just keeps on running, right, as though the exception never happened. The exception has been handled, right? We dealt with it, and it's gone. Right? We can just keep on going. Now, suppose we want to know what went wrong. There is a more complicated syntax for the catch block, and it looks like this. So we have a try, and then the block that we wish to protect by the try. The protected block is the block of code where if an exception occurs in that block, it will be handled. And then we can have a whole series of catches. And every catch can have in round parens the type of an exception that we would like to catch, and optionally a variable name if we want to interrogate the exception that's thrown. And then each of those catch blocks can have statements. And what happens is when the exception is thrown, the runtime determines a single catch block that is the best catch block to handle this exception. So let's take a look at an example of that. Right. So here, we're going to do this again. We're going to try to read our file. And this time I've said, I would like to catch an exception. So this is the type, and this is the variable. So when the exception happens, put a reference to an object that describes the exception into the variable exception, and that is a variable of type exception. All right, and now we can interrogate this thing. Instead of producing the dialog box that, again, we should be very familiar with, we can say, well, what would that dialog box have said? Well, it would have said, could not find this file. Right? And we can ask all kinds of things about this exception. Right? There's a ton of information in here about what went wrong and why it went wrong and where it went wrong and all of that. And I'm not going to dig into all of that. You can look at the documentation for exception, or you can explore it using IntelliSense, figure out what all of that stuff is. We'll talk about a few more of the properties of exception in a little bit. All right, so what if we want to do something different in different exception cases? So let's try this one more time. It's going to fail again. And this time, I've created a whole pile of catch blocks. So I've got a catch block for the file was not found, the directory was not found, there was a security failure, so there was no authorization for this file, even if it was found, or anything else went wrong. So the exception class is the sort of the base of all of the other exceptions. It is the catch-all for all of them. So in this case, we are going to transfer control to this first block, the file not found. And then we can look at this exception. And inside the block, once again, we can see that this is the exception for the file was not found. And there'll be information in there about which file was not found and all of that kind of thing. Right? We could have specialized error handlers for each one of these possible cases here. All right. The identifier here, each one of these exceptions, you'll notice that it has a green underline, green squiggly underline, indicating that there's a warning happening here. If we stop the code, then we can see that the warning is the variable exception is declared but never used. And in fact, that's true. We said, oh, we would like to examine what's in this thing, but we're not going to actually use it. If you used it in here, right, then the squiggly would go away. You notice that we are allowed to name all of these things the same. These are all local variables, but they are all considered to be in distinct local variable declaration spaces. So that's good, because you would very often not want to try to come up with separate names for each of these. If you really do not care about the contents, you just care about which exception type it was, you can just delete that. Right? And this just says, I just want to catch a file not found exception. This is one of the very few places in C# where you can say, I want to have a type and a variable name, or just a type. And you can get rid of all of these if you want, if you don't use the local variable inside the catch block. All right. Oh, and this catch exception, or this, right, which also catches everything. The sort of blank catch will catch any exception that's thrown. they must come last. And that is, as sort of C# requires that to give you sort of a visual hint of, we're going to run down this list and we're going to find the first one that matches, and that's going to be the handler. So C# makes sure that more general exceptions always come after less general exceptions. And in fact, if we tried to do something like put exception first, then you'd see we would get an error message that says here, a previous catch clause already catches all exceptions of this or a super type. We'll talk about what super type means in a later video. But basically, it's saying this is a more general exception than this one is. And therefore, by the time we get here, this one's already been caught. Right? So this always goes at the end. If you have both a catch exception and a catch that's just blank, you get a warning, not an error, that says a previous catch clause already catches all exceptions. This is actually legal for a bizarre historical reason. The bizarre historical reason was that in early versions of .NET, it was legal to throw things that were not exceptions. If you wanted to throw the number 12, you could do it, and the only way you could catch it would be like this in C#. In modern versions of .NET, if you attempt to throw the number 12, then it automatically synthesizes an exception around that thing so that it can be caught normally. So that's the reason why this syntax is still legal, but a warning. It's for bizarre code back from the C#1 era. So don't ever write code like this. If you want to catch all exceptions, just write that. That's the best way to do it. All right, so what's the right thing to do here? How should we correctly use try-catch in code? The most important rules are, first, only try-catch if you actually know how to handle the exception. Right? You know that something has gone wrong, and I need to handle it so that my program can keep on running. Now, we're going to see in a little bit some ways that you can write exception handlers that basically say, I want something to happen when this exception occurs, but I don't actually know how to handle it. Somebody else knows how to handle it. That's sort of a more advanced scenario. We'll talk about that soon. So number one, only catch things that you actually know how to handle. If you don't know how to handle a problem, don't say that you do. And don't attempt to catch boneheaded or fatal exceptions. If you catch a boneheaded exception, you are hiding somebody's bug. Right? You're saying, I am going to accept the fact that somebody is going to dereference null, and I'm going to handle that and keep on running, when the code that did that is wrong and buggy and should be fixed. You shouldn't be hiding their mistake. You should be calling attention to it so that they can fix it. And catching fatal exceptions is, again, just like sweeping the floors before the house is demolished. Really probably not a very good idea and kind of dangerous. You should just get the heck out of the house. So I want to talk a little bit about how method calls work with exceptions, because this is where things start to get a little bit weird. So I'm going to put a breakpoint down here, start this program. And I'm going to put a breakpoint in this catch block. All right, so we're going to call do something. We're going to pass in a file name. And apparently, we've got a catch block here. So let's step into do something and see what it does. Oh, do something also contains a try-catch block. OK, well, this is interesting. Let's see what's going to happen here. So we're going to try to read all of the text in this non-existent file and then write out the contents. But we're not going to get here because this is going to throw. So when we throw, what's going to happen? Well, control is going to immediately transfer to the appropriate catch. But we're going to throw file not found. This catch only catches directory not found. So what's going to happen? Well, we throw. Control is immediately transferred to the catch block in the method that called do something. So the interesting thing here is that try-catches are essentially non-local transfer of control. So far, every transfer of control we've seen has either been call a method, run the code in the method for a little while, then return. Right? So that's a very strict non-local transfer of control. You transfer control from one method to another and then back again. Or we have seen transfers of control within a method where we say, if, and then we branch to either the consequence or to the alternative of the if. Very local flow of control. Try-catch introduces a totally non-local flow of control, where something can go wrong in one method and control immediately transfers back to another method. All right. So once we're in here, we have a catch block that can catch every exception, and sure enough, we can write that out. Now here is an interesting feature of exceptions. Exceptions keep track of what did the stack window look like, this window right here. What did it look like at the moment that the exception was thrown? Not at the moment the exception was created, but the moment the exception was thrown. And that's a subtle distinction that I might talk a bit more about in a little bit. If we look at the console window here, you can see, sure enough, it looks just like the stack window does, right? It says that the exception happened. You usually read these things from the bottom up. We started with program.main called program.doSomething, and then we have all of this stuff in here. So we see that do something called read all text. We know that. Well, read all text apparently called something called internal read all text. And that called something else, and that called something else, and that called something else. And eventually that called Windows input-output error. And that is the thing that actually did the throw, right? So when the throw happened, not only did we branch from the method that we were in, do something, back to its caller, main, we actually branched from WinIO error, 8 or 9 levels deep, immediately back to our caller, right? So this is a very, very non-local flow of control. So, interesting question. What if there is no enclosing try? Or what if there is an enclosing try, but it doesn't have an appropriate catch? Well, if that happens, then the same thing happens that has happened every other time that we've had an exception where there was no try around it. You get, if you're in the debugger, you get a dialog box that says, hey, an exception was thrown right here. Do you want to debug it? If you're not in the debugger, then the operating system will produce a message that says an unhandled exception has happened in this program. We're going to report that to the standard Microsoft error reporting. Do you want to attach a debugger to it if you're a software developer, and so on. Basically, it's implementation-defined behavior. If you have a program that has an unhandled exception, all bets are off. The program is broken. It's going to crash and die. And if some good things happen, then some good things happen. And if they don't, they don't. All right. So I mentioned before, I'm going to talk about the scenario where you want to take some action, like say I want to log the fact that an error happened, but I don't actually know how to handle the error, right? Maybe some other code knows how to recover from this error, but all I care about is that I have a failure that I want to log. So let's take a look at how to deal with that situation. So once again, here I have a try catch block. I'm going to call do something else, so different method this time. And I'm going to catch any file not found exception that happened here and write it out. All right, well, what is do something else going to do? Well, this guy also contains a try catch block. It's going to have the try protected region, right, where it tries to do something that it thinks might fail. If a failure happens, it will catch any exception. It will write that exception out to the debug console. It'll write it out to this little window down here, the debug output window, which is a useful debugging tool. But I want to say, you know what, if an exception happens here, my caller is going to handle it. But while I'm debugging this code, I'd like a message to pop up that says an exception just occurred and what it was. But I don't intend to actually handle the exception here. I intend to handle the exception somewhere else. So let's take a look at what this does. We try to read the text. We branch immediately to the appropriate catch block, right? Not the catch block on our caller, because this one catches the exception, right? This is the most enclosing catch block that works. We write the message out to the console, right? So there it goes there. Could not find that file. Now here we have throw. Now every time that we've seen throw before, we've said throw new exception, and an exception constructor. We're not doing that this time. We're just saying throw. We're, in particular, not saying throw exception. We could say throw exception. We have an exception object in hand. We can throw it, right? What this does is this says, this catch block did not actually handle this exception. Run the code that's in the catch block, and then pretend that this catch block did not catch the exception, rethrow it. So what happens is the runtime starts looking again for, is there a catch block that can handle this exception? And sure enough, there is. The catch block in the outer try can handle the file not found exception. And then it does whatever thing is appropriate. The reason why I said to use throw and not throw exception is because, remember I pointed out that the exception has a stack trace associated with it. The stack trace identifies what the stack trace window looked like at the point where the exception was last thrown, not at the point where it was created. So if you say throw exception in here, if you just said throw exception, right, then the stack trace property of that exception would indicate that do something else through this exception, when in fact, file.readAllText, and then one of its callees ultimately through that exception. So you would lose information. So it's almost always the right thing to do to say throw and not throw exception. I want to talk about two more small features that were added to C# 6 that help with exception handling. One is called nameof, and the other is called exception filters. So here I'm going to demonstrate both of them. I'll take a look at nameof first. So I'm going to call this method demonstrate nameof. I'm going to pass in a file name, and I'm going to do that wrapped in a try-catch block. So if I step in here, I'm going to say, well, if the file name is null, throw an argument null exception. Oh, wait, this is different. Before, when we wrote this code, we just had the string file name in here. Now I have this name of file name. And basically, what this is doing is this is just the same as this. This is just another way to write this string literal. So of what possible use is it? Well, I'm going to hit stop here. The possible use is, suppose I highlight this file name here. You'll notice that this was highlighted, this was highlighted, this was highlighted, this was highlighted, this was not highlighted. Right? As far as C# is concerned, this is just a string literal, whereas every one of these things that are highlighted is a usage of this local variable, or this parameter, actually. So that's one reason why it's useful. If I rename this thing, if I decide that this really should be file name with a capital N, you'll notice all of them renamed, but the string doesn't rename down here unless I click on this little include strings checkbox. And there might be a string that contains the word file name that I don't want to rename, right? So, and it might rename it by accident. So there's it's a very small feature, but it's very handy. It allows you to treat the name of anything, in this case a parameter, but a local variable, a method, a class, whatever. It allows you to treat the name of anything as a string, without using a string literal that would then be difficult to use the find all references of this variable feature. So that's the deal with nameof. And now let me talk to you a bit about how exception filters work. So we'll start this program up again. All right, so we'll step into demonstrate nameof. All right, so now, once again, I'm going to try to read the contents of a non-existent file and write them out. And once again, I have a debug log here that then just simply rethrows. You notice I've used the name of feature again down here in my log to say it was the demonstrate nameof method that produced this exception. This is a kind of a nice little thing to do. And again, if I were to rename this method, then it would automatically rename it down here too. So another nice usage of that feature. The bit that I want to illustrate, though, here is when I do this rethrow, what's going to happen? I have a catch block up here that could possibly catch this exception. But suppose the method that I'm calling, demonstrate nameof, suppose it does a whole bunch of stuff. And some of that stuff could produce file not found exceptions For files that are completely unrelated to the file name that I passed in, I might want to say, I only want to catch this exception if the condition is met that the exception is actually about the file that I care about. And so C# 6 adds a new feature that allows you to do that very easily, which is after the catch block, you can then say when, and then have a condition in here. And if the condition is met, then the catch block actually handles the exception. If the condition is not met, then the catch block does not handle the exception, and the runtime keeps on looking for a catch block that does work. So I said before that I told you a small lie, then that the lie was that control transfers directly to the catch block that handles the exception. And now we know what the lie was. Control actually transfers to the exception filter first. The exception filter is executed to see if it returns true or false. And if it produces true, then control is transferred to the catch block. Otherwise, the runtime keeps on searching for the appropriate block. Next time, we will see another way in which control does not go directly to the catch block. So summing up, you got to handle exogenous exceptions. If you don't, your program will probably crash someday. And you got to keep in mind that the world is an imperfect place. People unplug network cables. People have disks that fill up. All these kinds of things happen. There's not much you can do about it. You got to write programs that deal with it. Don't handle boneheaded or fatal exceptions. If an exception is easily avoidable by doing a simple check, and you can't guarantee that the check will always be true, then you need to do the check. You need to check if things are null before you dereference them, unless you absolutely know that the thing is not null. Only handle exceptions that you know how to recover from. If there's an exception that you want to handle for purposes of logging or whatever, make sure you rethrow the exception. Don't just eat it, so that code that's above you on the stack can possibly handle it. Catch blocks allow you great flexibility in the way that you can handle exceptions, particularly now that exception filters have been added to C# 6. Funny story about exception filters. Visual Basic has had exception filters for many, many years. The chief designers of C# always resisted adding them to C# because they didn't think it was a very good feature. One day, somebody asked Anders if they could add exception filters to C#. Anders Helsberg, the chief engineer of C#, he said, "What is it going to take to make you stop asking me that question?" And they said, "What it's going to take is you actually doing it." And so finally he gave in C# 6. Exception filters are now part of the language, and they're kind of nice. And you can use the name of operator in C# 6. Totally simple little operator, but it's very handy for these scenarios where you've got a string that would contain the name of a method or a parameter or something like that. I will try to use it throughout the rest of the code samples that I display, but I'm not in the habit of using it because it's a brand new feature. So if I slip up, don't be too mad.